Hello everyone and welcome to our webinar. My name is Marina Silva and I'm representing Integrated Global Services, or IGS for short. I'm joining you here from England, and just so we know that you can hear us and you can see us, could you please type in the chat where are you joining us from today? And I'll get this started. In this webinar, we will talk to you about holistic approach to corrosion in sour amine systems. And first and foremost, let's say hello to our speakers. We have Philippe Lagrange, senior engineer from Sulfur Experts.
Hello, everyone.
Hi, Philip, and he will talk to you about trends in tragedy, an analysis of 131 corrosion failures in amine systems. Then we have Tim Miller, the former director and chief executive at Tengiz Chevroil and currently executive director at IGS. Tim will dive into lessons learned at the TCO facility in Kazakhstan with regards to corrosion in amine vessels. Tim is not joining us live this morning. Colin Bateman will do the Q&A for his presentation. And then we have Colin Bateman, corrosion mitigation expert from Integrated Global Services.
Good morning, everybody. Well, good afternoon.
And Colin will discuss failures and successes of corrosion barrier systems. Then we have Mustafa Daoud, Senior Technical Specialist from PAL Corporation.
Hello, everyone.
And Mustafa will tell us how to improve amine plant reliability through fluid contamination control. Then we have Jacques van Velen, Sales and Marketing Manager from MPR Services.
Very good morning, everybody.
And hi, Jacques. And Jacques will discuss reclaiming amine solvents. And last but not least, we have Mike Shalen, Principal Engineer from Sulfur and Amine Experts. Mike is not joining us live, but he may join us later for the Q&A for his presentation. And he will talk about the effect of hydraulic flow on amine plant corrosion. It looks like everybody can see us and hear us okay. The webinar will take about 2 to 2.5 hours in total and will contain presentations, interactive question and answer sessions, and polls. So keep an eye on the polls area when the new polls come up and contribute. You can ask your questions in the questions tab on your right. And there will be a 5-minute Q&A after each presentation. Any questions that are not answered during the live Q&A, the speakers will type their answers underneath your question after the presentation is over. You're also welcome to upvote each other's questions if they seem of interest, and then we will go over those in more detail during a roundtable discussion at the end of the event, where we will also review the answers to polls. Some housekeeping before we start. We are broadcasting live. If you experience any technical difficulties, if you lose connection, sound, or image, try refreshing your browser or switch to a Google Chrome browser or connect using your mobile connection. Or you can dial into the webinar to get the audio. I'll post the phone numbers you can call in the chat now, and you will need a dial-in code as well. And if for some reason everything's going wrong, you can't get online, the recording of this webinar will be available on this same link. It will take a while for it to upload because it's going to be a large video, but if you refresh the browser once this event is over, in about half an hour to 1 hour, the recording will be there. Excellent. So without further ado, we will start with Philippe Lagrange's presentation, Trends in Tragedy.
Welcome to the Amine Experts webinar on why Amine systems fail. In this webinar, we're going to go through the root causes behind 400 different Amine system failures. We're going to look at the trends, what goes wrong most often, and it is my hope that you can use this information to focus attention on your facility, on the root causes of problems that are most likely to occur, and thus prevent them from occurring and dramatically increase the reliability of your Amine system. Amine systems are widely used throughout the oil and gas, steel, biogas, carbon capture, ammonia production industries to remove CO2 and H2S predominantly from hydrocarbon streams. Now, maximizing the sort of reliability of these Amine systems, maximizing their time, on stream producing can be a challenge. In fact, in our investigations, we've actually found 60 different reasons that could cause a production failure in an Amine system. So, getting down to, which problems you need to worry about and which are very sort of rare and exotic things that you can mostly ignore is quite important for the industry. So with this in mind, we built a database of all the past investigations we've done into Amine system failures. And in order for a case to be put in our database, there had to have been a major production failure, so significant loss of production leading to loss in revenue. So the costs of these incidences actually ranged anywhere from $100,000, was kind of our minimum threshold, all the way up to, in one particularly severe instance, $250 million US. So you can easily imagine that with 400 of these instances, this database represents billions of dollars of loss to industry. So in the database, it's primarily composed of investigations done by my colleagues and myself when we go on site and troubleshoot. There are also around 100 papers from external sources, and in order for one of these external sources where we didn't have the full background to be included, we had to see that the paper had sort of dug into depth and gone through all the various potential root causes for the problem in question. A paper that just has an offhand statement like we had bicene and thus we had corrosion, we can't include that because we can't see that a full investigation has been done. So yeah, thank you to all the external authors as well, who've actually published their work in enough detail that it can be of value to the industry. Now, when we look at what can go wrong, we see that broadly there's sort of three general categories of what goes wrong most often. And if you've been working with Amine systems for a while, this will probably not be a surprise, but it is corrosion, off-specification, product, and foaming. And we're going to dig into each of these in more detail as this talk progresses and we go into all the sub-root causes. Now, the first trend that we actually saw was that there was a difference between plants that were predominantly processing CO2 and those where there was significant H2S present in the feed gas. And that difference really was the proportion of failures that was caused by corrosion. So in CO2 service, more production failures were observed as a result of corrosion than in service where H2S was in the feed. And this difference is quite important when you're looking at these different systems. So the first thing we're going to talk about is corrosion. Now, there are many different mechanisms by which corrosion can occur and many things that can promote corrosion. These are described in detail in the paper that is presented with this presentation. But one of the really complicating factors with corrosion is there are often multiple factors that will contribute to a corrosion instance. And that is what makes it actually the most difficult of the three main failure types for us to troubleshoot. So broadly speaking, we can divide corrosive failures up into three different categories. So design, operation, and hygiene. And when we look at this trend, what we see is that two sort of root causes really stand out, and that's understripping and high heat stable salts. So I'm going to dig into those, but first we're going to take a look at where corrosion occurs. So the bulk of the corrosion in the amine system occurs in the hot section, so the bottom of the regenerator column and the reboiler, which accounts for almost half of the 131 corrosive failures that we've seen. And this makes sense because corrosion is a chemical reaction and the kinetics of it increase with temperature. So the higher temperature parts of the plant are going to corrode faster. So the first and really one of the most preventable types of failures that accounts for a large number of the production failures that we've seen, especially when there's a reboiler tube leak, hole in the reboiler shell, vapor return line, bottom of the stripper, is what we call understripping. And that really just means that there's not enough heat duty going into the amine to regenerate it properly. So you will still have a lot of CO2 left in the amine. And even if you're on, say, a refinery amine system where there's very little CO2, the CO2 is actually a stronger acid than H2S. So you could end up stripping out most of the H2S, but you'll still be left with the CO2 in the lean amine. And this CO2, when it gets trapped in sort of stagnant areas, especially among your reboiler tubes, where it's not as easy for gas to escape from the liquid as it is on a tray in the regenerator, say, can result in very aggressive corrosion. So really this corrosion mechanism occurs when you are stripping the bulk of the CO2 from your amine in the bottom of the regenerator column and in the reboiler, rather than in the actual bulk or in the main section of the regenerator column. You want a nice even stripping profile with CO2 being removed throughout the column. You don't want to be doing a lot of stripping in your kettle reboiler, for instance. So this really occurs when you're not putting in enough heat duty, and it can also occur when there's cold, rich amine being fed to the column. So if you have a very inefficient or undersized or fouled lean rich exchanger, you can send cold rich amine, and that will use up heat to heat it up, and your top couple of trays in your regenerator column will then not be doing stripping, they'll be heating the amine up. Could also take place as a result of running the regenerator column with too high a pressure, though this is a little bit more unusual. What it looks like, so it has what we call a sort of typical pitted appearance. It really looks like a mouse has taken a bite out of some cheese. The CO2 has taken a bite out of some of your metal. So here's some typical examples of CO2 attack on carbon steel metallurgy. By the way, this corrosion mechanism can also occur in stainless steel. Stainless is not immune, it's just a little bit more resistant. Now, the other dominant sort of main cause of corrosion that we see in amine systems is high heat stable salts. So what heat stable salts are briefly, they're acids that are stronger than H2S and CO2 that have entered your system, and they bond to the amine. And because they're stronger, that amine acid bond doesn't easily regenerate, so it's called heat stable. It doesn't regenerate, it just accumulates in your system. And when these levels of these acids rises too high, the solution becomes corrosive, and typically it'll look something like this, sort of like a lake of corrosion. This is the operators of this plant called this the moose head. Every shutdown they opened up bottom tray of their regenerator, they see what looks like a moose head. It's actually heat-stable salts that have corroded this section of the plant. And historically, there was this sort of limitation of, say, 10%. I mean, historically, back in the dark ages, the 1980s, they'd say 10% of amine strength was the maximum level of heat-stable salts. And when MDEA and sort of other higher strength amines, came to market, that no longer held. We found carbon steel could not really handle higher concentrations like 4 or 5% of heat-stable salts. So now the industry's moved to sort of 3% limit as your maximum heat-stable salts. And when we looked in detail at the failures that we'd seen, we saw that generally this 3% limit held true. We did not see many failures below 3%. And where we did see failures below 3%, there were sort of two specific conditions. So the two exceptions to the 3% rule are sweet systems, so systems with a lot of CO2, and MDEA. So MDEA is actually the weakest of the amines, and when it's in the CO2 system, it is more vulnerable to attack by heat-stable salts. So MDEA systems, generally, you may want a slightly lower level, a lower limit for heat-stable salts. And the other exception we saw is when you had high tray spacing. So in the industry, there's this sort of general 600 millimeter, 2 feet space between the trays in your regenerators and absorbers. And we found that we saw corrosion in situations where there was a higher than this 2 feet tray spacing. It is unusual, but you do sometimes get systems with higher tray spacings. And these systems did appear more vulnerable to attack by heat-stable salts. So if you're running MDEA or a system with high tray spacing, you may want a lower limit, say 1.5% maximum heat-stable salts. Now, in order to sort of not overlook something that's important to be aware of, I'm going to talk a little bit about hydrogen-induced cracking. If I'd given this presentation 40 years ago, this would have been the number one reason. It used to cause many, many failures in amine systems, and some of them were, extremely high profile and kill people. And a lot of industry attention has been given to this as a result of the problems caused by it. And so we see far less hydrogen-induced cracking amine system failures today than we have historically, which is a very good thing. And there's sort of two ways this is prevented. One is by using a certain standards of steel, and the other is by doing something called post-weld heat treatment. And both of these make it a lot more difficult for hydrogen-induced cracking to occur. And the details of the mechanism are explained more in the corrosion sections of our amine course and in the paper.
Philip, thank you very much for the presentation. We will now commence our question and answer session. So if you haven't asked your question yet, please type it in the questions tab and we will address it live right now. So our first question for you, Philip, is from Rob. Are these corrosion issues specific to CO2-only systems, or is the distribution of issues the same for CO2 and H2S?
So the distribution is not the same for CO2 and H2S. Some of the problems are common. I mean, the most common corrosion mechanism we see is sort of CO2 attack, CO2 pitting in reboilers in the bottom of amine regenerators or stripper columns. And we'll see that in a refinery with a lot of H2S, and we'll also see it in a carbon capture plant. So some of the mechanisms are common, whereas some of the other ones, for instance, sulfide corroding your overhead system, you need ammonia in your feed. So that's predominantly refineries and a couple of other applications for industries where there's ammonia and the gas being fed to the amine system. But you won't see that corrosion mechanism in the natural gas industry, for instance. So there are some differences, but the two biggest corrosion mechanisms, the most common, which are sort of CO2 pitting and heat stable salts. Those occur in pretty much all amine systems that are out there.
Thank you, Philip. Our next question is from Ali. Why do we have HSAS and how can we reduce this?
So I won't take too much of Shark's thunder. He's going to be doing a talk fully focused on this topic, but heat stable salts occur because you get something into this, normally because you get something into the system that's acidic, so you've got oxygen going into the system or hydrogen cyanide. If that enters the system, it'll form a heat stable salt. And because it's a fairly strong acid, you're going to not be able to get it out the system. So it just accumulates. So even if you have a small amount of, say, oxygen in your feed gas, you can sort of build up a fairly high level of heat stable salts fairly quickly.
Thank you, Philip. A question from Amit. Is hydrogen bakeout required for all thickness, or is it required only for higher thickness material?
That sounds like a metallurgy question for which one of the other presenters would be better able to answer. Yeah.
So we'll wait for Colin's presentation later on.
Yeah, I think so.
Thank you. Question from Abdurrahman. In FCC unit, what is the best product to use, MEA or MDEA?
Depends on it would depend on what pressure you're operating at. Well, there are a lot of considerations that go into what amine to use. Generally, MEA is quite old-fashioned, so we wouldn't build a new plant with MEA, generally speaking. But one of the challenges of switching away from MEA to MDEA is that the MEA is a very strong base and can treat at very low pressures. So if you have a low pressure fuel gas absorber and need to meet a tight specification, it can be a challenge to switch from MEA to MDEA, even though there's usually some corrosion advantages and other advantages in doing so. So it's really a sort of something the case needs to be looked into in a little bit more detail. Yeah.
Thank you, Philip. A question from Andre. How high can the oxygen be, for example, parts per million or ppb, ingress of that allowed before excessive amine degradation and corrosion will happen?
So there's sort of a threshold. Shark will probably give a more detailed answer, but the oxygen is only soluble to a few ppm in the amine. So once you go above this limit, you don't really see a big difference. That said, you want to ideally eliminate oxygen as far as possible from your feed gas. So ideally, you want to get it down to parts per billion level. But sometimes this can be quite a challenge. It really depends from where the gas that's getting treated is coming from, and if eliminating it's possible. One thing to be aware of is often with we get this question with makeup water and storage tanks. Should the storage tank be nitrogen blanketed? Does the makeup water need to be de-aerated? And one thing to be aware of is usually the reaction of oxygen with amine won't happen below 60 Celsius. So when you have, if you have a storage tank in the Middle East, for instance, that you don't have heating elements in it, that probably doesn't need a nitrogen blanket. Whereas, if you have the same storage tank in Canada with heating elements in it, heating coils in it, then you probably do need a nitrogen blanket, because then the oxygen will react with the amine at those higher temperatures that the heating coils can reach.
Thank you, Philip. Next question is about heat stable salts formation. Is it a one-time process or is it a continuous process?
Normally it's a continuous process. So you have a small, can be 1 ppm of say, of oxygen or acetate or something coming into the system, and over time it'll build up. That you can have incidents where you have a sudden high buildup of heat-stable salts. For instance, if you get a slug of well water, well brine from down a gas well, so sort of the slug of that liquid comes into the system, or you have what's called SO2 breakthrough on a tail gas unit. So there are certain circumstances where something goes wrong operationally, and a large dose of something that shouldn't be in the amine system gets into it. And then that's often linked to very severe corrosion, unless the plant catches that it's happened fast and does something to address it.
Thank you, Philip. Question from Amela. Post-weld heat treatment. Will the treatment be applied in accordance to API 945?
It depends where you are. So the different countries have different standards. The API 945 is the most commonly used in the industry. So yes, some regions will have slightly different procedures. But the important thing is that it's done in a sort of in a good and professional way. No other than just not done. We normally when almost all the welds we see these days are post-weld heat treated. Normally it's a fairly old plant if they're not heat treated. So sort of legacy welds from the 1970s or something.
Thank you, Philip. A question from Rob. Do you have guidance on rich and lean loadings, for MDEA, with particular focus on avoiding amine cracking on the lean line?
So we do have guidelines. They will vary depending on whether it's activated MDEA, so it's got MDEA with piperazine, or just MDEA, and if it's CO2 or H2S service. Normally it's done to limit sort of breakout of acid gases. So if you have amine, it holds the H2S and the CO2, but once it starts getting very loaded up, it doesn't hold it as well or as strong, and as it passes through the pipes and through the heat exchangers, there's pressure drop, there's temperature increase, and some of that H2S and CO2 can break free from the amine solution, and you can get very aggressive corrosion. So for that reason, we put limits on the amines, and there are different limits depending on the amine and the service. But it's not really done to prevent cracking in MDA system. It's more done to prevent pitting. So the limits for all the different cases should be in the paper that's sort of associated with this talk, and anyone who would like to get hold of that paper can just drop us an email. We'll happily share it. I won't list them all off now. It's about 20 different things depending on what the amine is and what the service is.
Thank you, Philip. And we'll take one more question before moving on to the next presentation. But Philip will also be addressing any unanswered questions by typing the answer underneath each one. So question from Georgi. What about cyanide present in the OVH system at the regenerator? Does it cause serious corrosion? And are there any industrial limits for cyanide concentration to be met?
So yes, cyanide can cause quite serious corrosion. If you're talking about cyanide entering with the feed gas, almost all of it gets absorbed by the amine. We've done some testing around it, and so almost in the plants we've tested, almost all the cyanide gets absorbed down to less than 1 ppm in the outlet gas. About 60% of that cyanide converts, if it's an H2S system, amine system, so for instance a refinery FCC, about 60% of that cyanide converts to heat stable salts. So that's well, you're creating a heat stable salts which can cause corrosion, but also the cyanide itself, if it builds up if it gets trapped in the overhead system and builds up, can also cause. We don't see it a huge amount on amine systems. It's more common for sour water strippers. But yeah, for sure, the cyanide's what's called a chelant, and can make it and can sort of dissolve any passivation layer you have on the metal, and make corrosion a lot more aggressive. So if you already have a corrosion mechanism in the overhead, a lot of ammonium bisulfide, and you add a lot of cyanide to that, the corrosion can accelerate quite rapidly. We don't have a sort of industry maximum limit number that I can give you. It's more about the experience of the plant. If you see a lot of corrosion and you think it's a result of this, then it might be time to look at dosing cyanide neutralizer or a corrosion inhibitor or something like that.
Thank you, Philip. We will now move on to the next. Yeah.
Cyanide. I don't know. I was going to say.
I think Philip has briefly lost connection, but that was our last question for now. We'll now move on to the next presentation that will be delivered by Tim Miller. And Tim will dive into lessons learned at the Tengiz Chevroil facility in Kazakhstan with regards to corrosion in Amine vessels.
Good day, everyone. My name is Tim Miller. As you can see from the slide that introduces this section, I worked for Chevron for more than 38 years. I worked in Kazakhstan for the last 8 years of my career, 5 years as a general director of Tengiz Chevroil, and 3 years as managing director of the Eurasia business unit. Since my retirement from Chevron in 2019, I've worked for Integrated Global Services in the role of executive director of the Republic of Kazakhstan and also as an operations advisor worldwide for the company. I also serve on several boards of directors, including the National Oil Company of Kazakhstan, Kazmunagas. In this presentation, I'll give you a little orientation on the country of Kazakhstan, on the company Tengiz Chevroil, and then I'll cover a case history of a sour amine system failure where TCO used Integrated Global Services technologies to clad the internal lining of the vessel to protect it from future damage. Before I introduce you to Tengiz Chevroil, I'd like to talk just a little bit about the country of Kazakhstan. Officially, the Republic of Kazakhstan is the world's largest landlocked country, and in fact, it's the 9th largest country in the world. Kazakhstan is the dominant nation of Central Asia economically, generating about 60% of the region's GDP, primarily through its oil and gas industry, but it also has vast mineral resources as well. Now, lowlands make up about 1/3 of Kazakhstan's huge expanse. Hilly plateaus and plains account for about half, and the low mountainous regions about 1/5. The western and southwestern parts of the republic are dominated by the low-lying Caspian Depression, which at its lowest point lies some 95 feet below sea level. The ancient Caspian sea bottom is where the Tengiz oil field was discovered in 1979, and that takes us to the company Tengiz Chevroil. The Tengiz reservoir holds about 26 billion barrels of oil and gas. It's very large, it's very deep, and has high sour gas content. The H2S content is about 6%. It is complex and difficult to operate. The operator of the Tengiz field is Tengiz Chevroil, a limited liability partnership that was formed in 1993 between the Republic of Kazakhstan and the Chevron Corporation. Over the years, Chevron and the Republic of Kazakhstan bought and sold different interests in the company Tengiz Chevroil. The current ownership is Chevron 50%, ExxonMobil 25%, Kazmunagas 20%, and Lukoil 5%. Kazmunagas is the national oil company of Kazakhstan, and of course Lukoil is a major Russian oil company. Tengiz Chevroil is a very prolific producer in Kazakhstan. The company generates about 1/3 of the country's total production, with crude production of 540,000 barrels a day from approximately 100 wells. The crude production per well is very high, and includes a significant amount of natural gas and natural gas liquids. 6 separate trains currently process the sour crude into marketable components of sweet crude oil, sweet natural gas liquids, and elemental sulfur. 4 of the trains are an old Soviet design called the Complex Technical Lines, or KTLs. A 5th KTL train of similar design was put online in 1997. And finally, the newest, the 2nd generation plant, accounting for about half the total production, was put online in 2008. With 6 trains in operation now, and the $45 billion 7th train being added now, the annual maintenance and turnaround programs are very important to Tingi Chevroil's success. Each year, 1 to 2 trains are taken down during the summer, representing between 25 and 50% of TCO's daily production. The full turnaround program each year usually lasts between 30 to 40 days in duration. So 135,000 to 270,000 barrels a day off for 40 days. You can imagine the cost of just a few hours of delay in the maintenance program. TCO's priorities for annual turnarounds are safe execution, reliable execution of the maintenance scope, long-term integrity of the maintenance work, and then finally costs. And now let me turn my attention to a particular vessel in our KTL plants, an amine regenerator column that was truly a bad actor for us. And I want to give you the bottom line, the good news. Because of the use of IGS technologies, we saw reduced life cycle costs. IGS technology and their high velocity thermal spray metal cladding provided an effective risk mitigation and a robust protection system. And we saw lost production opportunity savings of $17.4 million just in our first year as compared to the next best alternative. And in fact, compared to replacing the vessel in total, we saved $64.5 million. We were seeing pretty typical corrosion mechanism in this amine regenerator column, where we were having acid gas breakout at elevated temperatures and attacking the surface of the vessel. In some locations, we'd actually seen some pits penetrate through the shell wall. We'd had some sections cut out and replaced, but upon inspection, we're continuing to see corrosion issues. This vessel was quickly becoming a reliability and integrity problem for the plant. So we worked with IGS technology and developed a novel corrosion-resistant cladding system that acted as a barrier to prevent the H2S from contacting the base metal. The Tingi Chevroil turnaround team really had 3 viable options with respect to this vessel. One was to replace the entire vessel with a different metallurgy or a cladding system done in the manufacturing process. The second option was to do a weld overlay. Now that was expensive and slow, and it would put the turnaround schedule at risk. The third option was to use the IGS HVTS system that was installed in just about 65 hours. Now this fit quite nicely into the schedule. So IGS ended up coating a total of 40 square meters, including the horizontal and vertical trace supports, and this obviously worked out well, and it was just one of many successes in our turnaround. This is my final slide. You can see the results. The IGS high velocity thermal spray metal cladding system is just more economical than weld metal overlay due to time sensitivity and the need to fit into the turnaround window. The cost of the weld metal overlay is also 3 to 4 times higher, and the estimated life cycle savings, $64.5 million over a 3-year period. IGS has mitigated internal corrosion challenges now in 18 amine regenerator and contactor columns at Tingi Chevroil, protecting more than 2,000 square meters of surface area. Thank you very much for your time and attention. We look forward to your questions.
So I'd like to welcome on stage Mr. Colin Bateman. Tim is not with us this morning, but he will join us for the afternoon session. If you are joining both sessions, we're running this webinar again in how many hours, Colin?
It'll be 6 roughly.
In roughly 6 hours. That's right. Thank you. So if you have any questions about this presentation, please type them in to the questions tab. We'll just give it a minute. Maybe Colin can also comment on how TCO have previously mitigated corrosion in their vessels.
Sure.
Before they used HVTS.
To give some background, I mean, IGS have had a long-term relationship with Chevron, obviously working with them in the United States as well as in Kazakhstan. And when Tim mentioned about the development of a technology, it was truly a co-development. I mean, in the early 90s, IGS started doing applications with Chevron and Chevron facilities, and we saw some initial challenges with the technologies that were being used in terms of the thermal spray systems that were applied. And with the Chevron Technology Center, we actually embarked on a program to refine those systems and develop more robust systems for applications in these environments. And Kazakhstan is very particular in the sense that it's not an easy place to work. It's a location that's challenging in order to send your equipment and materials and your personnel. And you saw the very high opportunity costs they have in terms of time. So extended turnarounds meant significant cost to the plant from a production point of view. So prior to them using that technology, they were using temporary plugs in the column. They were having to do sectional replacement in the column, which was adding additional time to the turnarounds. As you'll see in the next presentation, the high velocity thermal spray systems as they're developed give that permanent barrier that can be applied in situ in the field in an efficient period of time so that we could meet their shutdown requirements. I mean, currently IGS, we have contracts in Kazakhstan with KPO, TCO, and NCOC, doing these types of work in not just the Amine columns, but other vessels in their facilities.
Thank you, Colin. And we'll have 2 questions about Tim's presentation, if you can answer those.
I'll try.
Question from Laxma. Is hydrogen bakeout mandatory before the application of HVTS?
No, absolutely not. And in some cases, it's not actually preferable, if that's the right word to use. We've done applications, for example, on, I can think of one that springs to mind, on a large deethanizer column where they had a hydrogen-induced cracking, initiation of that. And it was a column that was built in the 70s, so it wasn't built from Hick-resistant steel. And the client did a very detailed engineering investigation to see how they could maintain the integrity of the column. And they looked at doing hydrogen bakeout, but there were significant concerns that the baking out process would actually make the cracking worse and create more stepwise cracking in the internal steel of the column. So their intention then was to prevent any further generation of atomic hydrogen by stopping the corrosion taking place on the surface of the metal so that the situation didn't get any worse. So maintaining the existing integrity of the column for the long term by freezing the condition, if you like. And so they were able to do that by upgrading the internal metallurgy with a high velocity thermal spray system. So in that case, baking out the hydrogen was potentially a significant risk in destroying the vessel effectively and losing the integrity. So it's not required. It obviously depends on a case-by-case situation in terms of the specific conditions of the vessel, the amount of hydrogen you have, the amount of cracking you have, and whether that's considered a benefit or not, I guess, is up to the integrity engineers who are looking after the vessel.
Thank you, Colin. We'll take one more question before moving on to your presentation. Would HVTS only be applied to existing or also new build plants?
The reality is the economics, the real benefit, if you like, the value of HTS is in field applications. So the vast majority of the work that we do is in situ in brownfield. But that doesn't mean that it's not applicable for greenfield equipment. We have on occasion applied in new equipment, but that tends to be once it's been delivered to the client and they realize that they need to upgrade the internal metallurgy. From new, There are, shop applied technologies which can typically be more economical than bringing in a team to apply an HVTS system in a shop. So most of the work we do is on asset life extension or improving the existing protection in vessels that are operating and as such are brownfield vessels.
Thank you, Colin.
Okay.
And that segues us nicely into your next presentation,
Yep.
Which will be all about failures and successes of corrosion barrier systems.
Good morning or afternoon. My name is Colin Bateman. I work for IGS. Thank you to Philip and to Tim for their excellent presentations. What we would like to look at in this presentation is the different options you have in terms of corrosion barrier systems and what can be failing and successful approaches in applying a corrosion barrier system in the types of environments that we've discussed in the Amine system. So we're going to start with a very brief introduction to the topic. We're going to look at the types of barrier systems you can employ, and specifically the types of corrosion resistant alloys we can use or we would preferably select for this type of sour service. We'll look at how those alloys can be installed, different technologies for that, and then just run through some case histories of examples of applications in the field. As explained by Tim in his presentation, Amine units play a critical role in terms of the production, the output from a plant, and any breakdown in an Amine system or requirement for an emergency shutdown is very expensive because it directly reduces the output capacity of the facility, and obviously depending upon the size of that facility that can run into hundreds of millions of dollars as we talked about in the previous presentation. As Philip discussed, corrosion is widely seen as one of the principal reasons for these unplanned failures. So clearly an effective corrosion management process is key in order to maintain these assets and to maintain the uptime and the productivity. So how are we going to create this type of effective corrosion management system? We need to address these challenges. We need to make sure that we can identify and install a corrosion barrier system that's fit for purpose, that's robust, that's going to give us the performance that we need in these environments. As Philip discussed, in the Amine systems, we have a variety of different corrosion activities that are taking place, and we need to identify a corrosion barrier system that can manage in these different environments and ensure we have protection against these separate processes and types of metal wastage attack that are taking place. So we have our organic acids, which come in typically with the feed, combined with the heat stable salts, and then are released in, for example, the hotter parts of the process, like our amine reboilers. We've got our ammonia and hydrogen sulfide, which can accumulate in the top of the column, creating this aggressive concentration and corrosive environment. And then we have upstream of the amine system, if we have cracking systems, then we can introduce hydrogen cyanide, which can prevent, retard the generation of protective oxide layers and barriers and lead to cracking potentially in the units. So these bad actors are there in the process. We know they're there. We need to manage them by installing a barrier that is going to protect, not only in the high temperature regions, but also in regions where we have, for example, turbulence, velocities, where we can also see erosion, corrosion processes taking place and not just the pure corrosion. So the barrier system we employ needs to be suitable to operate in all these environments. So once we've started the process and we're in operation, we've got some quite stark choices in what we can do in order to upgrade our equipment, in order to make it more robust for the operating environment. We can obviously replace the equipment with a new design, which potentially has installed from manufacturing a high nobility material. We can install on-site organic linings or coatings. These tend to be temporary solutions. They don't tend to last through multiple turnaround events, and often they're not suitable for the high temperature range or the high temperature regions in these units. Weld metal overlay, we can install in the field a corrosion resistant alloy with weld metal overlay. This process does, however, induce a lot of heat into the substrate. We create heat affected zones. We can change the hardness of the substrate material, and that has to be post-weld heat treated in these units where we're dealing with H2S environments and with lethal service. Another alternative is to use a high velocity thermal spray or a thermal spray procedure in order to install this high nobility alloy. One of the key benefits of this system is we don't create these heat affected zones, and there's no requirement for post-weld heat treatment. But you have to be very careful about what type of thermal spray system you employ based upon the performance in the industry. So one of the first things we consider is what alloy we're going to install that is going to be suitable for the different environments we see in Amine systems. We look at the different alloys in the marketplace, and what comes to mind is a C276 or a Hastelloy based alloy, which has a very high pitting resistance equivalent number, high resistance to these operating environments, and is going to be effectively inert or non-reactive. Once we've selected that alloy, then we need to think about how do we install that in the field? How do we get that put into our vessel during a shutdown and turnaround? As we talked about, we've got a couple of options in terms of cladding, field weld overlay. Both these options create these heat affected zones and require post-weld heat treatment, which can often be a very lengthy procedure, particularly when we're talking about large columns or vessels like Amine columns. High velocity thermal spray is a potential solution. No heat affected zone, no post-weld heat treatment. However, high velocity thermal spray has to be the right class of technology to perform in these aggressive corrosive environments. So when we're thinking about thermal spray for application in these conditions, we need to consider that we're creating an impermeable barrier with that thermal spray process. So we're using an alloy, a C276 alloy, but we're putting it through a highly aggressive application procedure. We're melting it in the thermal spray gun. We're then projecting it through the atmosphere onto the surface. So there can be lots of changes to that alloy unless we control the application process, unless we control the alloy itself. So thermal spray processes and the class of technology we use are critical to see the long-term performance that we need. A low velocity system creates a very open microstructure which has opportunities for immediate permeation to the substrate, so that would lead to failure. High velocity systems, we create a denser microstructure, but if we don't control, for example, the oxide content, then those oxides are embedded into the system and create a weakness and a pathway to the substrate. If we have highly stressed materials, so when we apply thermal spray, we build up internal stress, then we can see cracking. So macro cracking straight to the substrate or micro cracking. In a corrosive environment, those cracks become pathways to the substrate that can then lead to failure of the system. So we have to use a system where the conveyance or the application equipment is specifically designed to install a very dense microstructure. So we eliminate these potential pathways to the substrate from a microstructural perspective, and we need to use a modified alloy. And the modification is to increase, for example, some of the alloy composition so that the oxidation that takes place during application doesn't affect the performance of that alloy in the environment. And we have to de-stress the applied system to avoid the issues with cracking, whether that's macro cracking or micro cracking, which would create pathways to the substrate. So by using a high velocity system with a modified alloy, we eliminate these weaknesses which we'd seen previously in thermal spray applications in the field. IGS as a company, we've lived through all of these different stages, and we've used these processes and learned from these processes in order to develop the systems we use today. So in the early 90s, we moved from low velocity to high velocity. In the early 2000s, we moved from unmodified alloy to a modified alloy. And in each case, it was from field applications and premature failures of these systems in these types of corrosive environments. Since about 2000, we've been using a high velocity system with a modified alloy. So let's look at some examples of case histories of thermal spray applications in the field. In the pictures you can see here on the left-hand side, we're applying a thermal spray, a high-velocity thermal spray barrier with a twin-wire arc system. On the right-hand side, there's an HVOF system. Both systems are high velocity. Both systems create a dense microstructure. High-velocity arc spray on the left is the more common system used because it's more robust. It applies a wider range of materials and is more suitable for field application. So the first example is a AGR, amine absorber column or tower. The client started to see aggressive pitting in the middle section of the tower. So they were getting breakout of the corrosive materials into this section of the tower, losing wall thickness and potentially getting to a point where they were going to have to do replacement, sectional replacement, or ultimately vessel replacement. They wanted to install a corrosion resistant alloy, and they wanted to look at the different techniques to do that. Field weld overlay was considered, but that was going to take too long and would also require the post-weld heat treatment, which they wanted to avoid. So we installed the high velocity thermal spray systems using an IGS technology and an IGS alloy. Those applications were done in 2011 and 2012. These were clients operating in the Middle East. We then went back into these vessels in each subsequent turnaround cycle. So when the original application is done, when you're using a high nobility alloy onto a lower nobility substrate or a non-ferrous alloy onto a ferrous substrate, you can directly measure the thickness of that material. So you can create a map of the application surface and then use that map in future inspections to see if there's been any change to the internal barrier condition. So we went back in 2015-16 and then 2019-20, and each subsequent 4-year turnaround to do full inspections. The system, as we said, is comprised of a high nobility alloy, Hastelloy-based material, which does not corrode in this environment. So the system was working perfectly well and was allowed to continue to operate. This next example, similar to the first one, it's a section of the column where you typically see aggressive pitting corrosion taking place. This is a DGA amine column in this case. What's different about this example, or slightly different story, is the fact that the client, during the operation of the vessel, believed that he had continuing internal corrosion taking place. So he took some NDT measurements externally and believed that he was seeing metal loss. So what IGS can do with the internal thermal spray is we can use external inspection techniques to pick up that the internal cladding is still in situ and still operating as required. So we demonstrated that to the client. They avoided having an emergency shutdown, carried on operating for another 2 years before having the official shutdown, doing an internal inspection and seeing that everything was in perfect condition. We then extended the area that was protected in this column. As well as the amine columns, the strippers, the absorbers, the regenerators, we also have the amine reboilers. So these are locations where we have high temperatures, we get potential breakout of these bad actors causing very aggressive localized corrosion and often erosion corrosion because of the turbulence and the fluid motion inside the vessel. So this is a typical example where you get a washout of the top of the column from your sort of 12 o'clock position outwards to 11 and 1 o'clock, and that's where you're losing significant metal. Again, installing a high velocity thermal spray system here will stop that corrosion activity taking place. It also has very good abrasion erosion resistance, so will resist the abrasion activity from the turbulent flow. So provide a long-term solution in these environments. Over the last 20 years, IGS has installed these high velocity thermal spray systems in lots of different amine columns, operating with different types of amine in different environments. But the overall result has been the long-term protection of the internal surfaces of these vessels against corrosion and erosion. So since 2000, we've approximately applied around about 3,000 square meters of surface area. So how do we measure a success of a corrosion barrier? Well, I think the key measure is going to be the return on investment of the installation of that barrier into your vessel. And when you think about that return on investment, you should think about the cost of ownership of that corrosion barrier, not just the cost of purchase. So over time, you have lots of additional costs that build up in terms of your operating of that particular vessel. That can be maintenance costs, it can be inspection costs, it can be knock-on effects from extended turnarounds on your production, etc. So when we think about success, we look at the return on investment of the installation of that corrosion barrier system and the savings that that can bring to you as a client. So for a corrosion barrier to be successful, it needs to bring these benefits to the purchaser. We need to reduce the downtime of the equipment, reduce the operating expenses, provide a high return on investment, and provide a solution that is going to effectively protect that vessel for the remaining design life, enabling the client to have an increased operating time, increased uptime, and to extend the time between intervention into that vessel. IGS provide our thermal spray services around the world. Wherever you are located, wherever you're listening to this presentation today, we can support you with our local infrastructure and strategically placed operations and support services. So please don't hesitate to get in contact with us, even if it's an emergency situation. I'm sure we can support you. So thank you very much for listening to the presentation. I hope that gave you a brief overview of the sort of the different technologies that are available in terms of corrosion barrier systems. I'll be very happy now or delighted to take any questions that you may have.
Thank you, Colin, for this excellent presentation. And we do have some questions for you. So the first question is from Werner. Is this application only applicable for H2S or for any corrosion mechanism?
It's really for any corrosion mechanism which the alloys we're applying are designed to manage. In other words, that they're not going to be corroded or attacked by that environment, which for an alloy like a Hastelloy C276 material is a very broad range of corrosion mechanisms. So no, it's not just restricted to one type of corrosion.
Thank you, Colin. Question from Zephania. Oh, that's for Philip. We'll address that later. Question from Andre. Unlike cladding that is normally quite thick, HVTS produces a thin layer of corrosion-resistant alloy coating on the surface. And his concern is, if there is a scratch on the coating, will it produce a severe galvanic corrosion because of high surface ratio?
Yeah, that's a very good question, and it's often a concern. First of all, we're applying a metallic barrier, so it's a very robust system. So you would have to supply a sufficient force or an impact to dent the underlying steel in order to damage the thermal spray cladding. In addition to that, we do look at situations, applications to ensure that we mitigate any potential risk of galvanic corrosion taking place. So, for example, we would come out of zones where you have full immersion, and we'll come out of areas where you could potentially create that corrosive activity between the dissimilar metals. In the vast majority of applications in amine columns, we don't tend to see the development of that type of corrosion cell for a number of reasons. Typically, it's because you don't have the electrolyte or the liquid available all the time to create the pathway for that method of corrosion to take place. But it's something we've obviously monitored closely. We've done a lot of applications in amine columns where we're just applying in sections of the column. And so we've got a lot of field experience of doing inspections and seeing that galvanic corrosion issue is not one that we need to be worried about.
Thank you, Colin. A question from Ejaz. Can this coating help us increase CO2 handling capacity?
I'm not sure. I would have to defer to somebody who's an expert in the operations of the equipment, like Philip. But what the cladding will do is obviously protect your substrate from the corrosion potential activity of the process. So it's probably going to help you to increase the uptime of the equipment, which conversely would help you produce more. But I don't know if specifically the installation of a barrier system like this actually would improve the operation of or the efficiency of the process.
Question from AJ. Do you think we can use these HVTS corrosion-resistant alloy coating in CO FCCU boilers with chrome molybdenum steel?
We do a lot of work in boilers. I mean, IGS, we worked in the power industry longer really than we have worked in oil and gas. We have a lot of experience with high temperature corrosion mechanisms. So I would say yes. It would depend upon the application itself. For example, in boilers, if you have a wall-to-wall, those are typically relatively easy to access and to protect. But if you have a bundle system or a tubular system, it's much more difficult and sometimes not possible to install a protective barrier on that in the field. So I would say yes, we could potentially have a solution. We don't just have one type of alloy that we install. At IGS, we have a whole range of different systems we use in different environments, and some of that's dictated by temperature. So in your high temperature environments, like for example, high temperature sulfidation, etc., we have a different alloy that we use compared to what we're installing in the Amine columns. But yes, please share some information with us, and we can certainly look at it and see if we have a solution for you.
Thank you, Colin. Question from Praveen. What is the thickness of the coating generally?
So the typical thickness is a nominal 500 microns with a minimum of 400. And that thickness is designed so that we generate sufficient microstructure to eliminate any potential pathways through to the substrate or any permeability. So we have a safety factor in there, but minimum 400, nominal 500. Once you've achieved that thickness, you've established your corrosion barrier. And after that, any greater thickness is typically only utilized if we have a high erosion abrasion zone where we're expecting to mechanically lose some thickness over time.
Thank you, Colin. Question from Danilo. What about sulfuric acid? Do you have an application for low concentration of sulfuric acid?
We do. Yes, we work in environments where we see dew point corrosion of sulfuric acid, both in the power sector as well as other process industries like oil and gas, etc. So yes, we do have solutions. Again, dependent upon temperature, environment, etc. But in the majority of cases, we have a surface barrier solution for that.
Thank you. Question from Ajaz. How many years before recoating?
I mean, typically, in a system or in a process where it's just a corrosion mechanism, if we install an alloy that's resistant to that mechanism, then the alloy won't corrode. So we've got columns in service now that have been operating more than 20 years, and we don't have to replace the system because there is no mechanism to break it down. If you have erosion abrasion taking place, then that's a different phenomena, because obviously you're mechanically removing the barrier, the protective layer, and it's ultimately is sacrificial. So in that case, we can monitor the rate of loss, and then we can always rebuild as required during shutdowns and turnarounds.
Question from Jainik. Do we need to apply HVTS in each shutdown? Can local repair be possible?
Local repair is possible. If, for example, you need to install some new internal furniture or weld something in the vessel, you'd need to locally remove the HVTS, and then we can locally repair it. One of the benefits of the system with the reduced internal stress is we can locally blast down to nothing and then repair that area having done the preparation. You shouldn't be considering you're going to have to repair the areas where we've already applied, unless, I say, it's very high abrasion erosion. So typically what we're doing in subsequent turnarounds, we're inspecting the applications we did before, and then we're often extending the areas where we've applied the protection in the vessels.
Thank you, Colin. We'll take one more question, and then the rest will be answered in the questions tab. Question from Laxma. Stainless steel thermal spray is an alternate economic choice instead of Hastelloy or Monel?
To be fair, when you look at the material quantity, it's a relatively small part of the cost when you think about the application on site in situ. And we like to use an alloy which we know has a wide range of corrosion resistance. So it's suitable for a wide range of operating environments. The other thing is using a non-ferrous alloy is preferable in terms of the quality of the alloy after it's been applied with a thermal spray process. So we talked in the presentation about how aggressive it is to melt an alloy and then spray it onto the surface. When you use ferrous alloys, you have a higher risk of component degradation or alloy degradation during that process due to oxidation. So using a non-ferrous alloy does also have advantages in terms of the quality of the material we deposit on the surface. And that's the reason why we focus on your nickel chrome moly materials, your hastelloy type materials.
Thank you very much, Colin, for your presentation and answering the questions.
You're welcome.
We will now move on to the next speaker. And our next speaker is Mustafa Daoud, Senior Technical Specialist at PAL Corporation, and he will tell us about how to improve Amine plant reliability through fluid contamination control.
Hello, everyone.
Not this one.
A very good day to you all, and thank you for your attendance. My name is Mustafa Daoud from PAL Corporation, based in the Middle East. I am honored today to present you the topic about improve amine plant reliability through fluid contamination control. Amine units are sensitive to fluid contamination. Presence of liquid hydrocarbons and solid particles are well-known foaming promoters. Therefore, it is crucial to eliminate them efficiently and consistently to avoid operational issues and improve plant reliability. Fluid cleanliness is an important topic, and it plays a huge paramount role in acid gas removal units in terms of reliability and performance. A vast study conducted by amine experts highlighted foaming are attributed mainly to feed contamination in 35% of cases and solvent contamination related problems in 25% of the cases. If you consider these two main root causes, you see that the attribution of foaming causes is more than half that is covered here. And we will highlight during the presentation that by way of retrofit or rental filtration services, a plant can enhance its reliability in the amine loop without having to invest, because we know it's a longer path in new filtration separation equipment. We see here a typical PNID of an amine unit, where you have typically a contactor or absorber to sweeten the sour gas, and then you have the amine solvent loop with amine regeneration in order to guarantee the cycles and that the amine has been removed all the acid from it, and it can attack a new cycle of sweetening. We are having here, as you see highlighted in blue, 4 locations where a filtration, a separation solution is handy, and it can help to bring the cleanliness of the amine loop to low sustained levels. We can act on the sour gas by a good specified and designed liquid gas coalescer. In the rich side of the amine loop, we might have also a solution that directly intercepts those contaminations, especially for the liquid hydrocarbons, by means of a liquid-liquid coalescer. And then in the lean amine side, which is a more traditional location, we may have on a slipstream a liquid particle filter. Usually it is followed by an activated charcoal bed, which is also followed by a guard filter downstream of it, and usually this is handling up to 25% of the loop capacity. From scientific laboratory services, a division within PAL that does field measurements and testing and supporting our customers, we have assembled our data from numerous sites where we measured solid contaminations. And when we bring all these results into a graph, we see that 75% of those solid contaminations are smaller than 10 micron. It can be much higher. It can reach 95% that are very fine. So you can see the contamination can be numerous, but can also be very fine in its particle size distribution. Hence, you need really an improved technology to get mitigations of the contamination and to remove them sustainably. A view to give you a comparative data between existing and different filtration technologies. Depending on the objective of the application, one can easily help himself by selecting the right technology. And we see in our case, we are having very fine particles, so we are at the right side, and we need high performance. And the solid handlings are acceptable. Because the solutions we are proposing with absolute rated filters have the capability to handle solids and to remove them in an absolute way. And that is very much important, and it's illustrated on the picture on the right side, where we can see a non-filtered sample was submitted to two filters. One was a 10 micron nominal, and the result is picture number 2. And one was an absolute rated filter, effluent, sample number 3. Directly visually, you can see the performance of filtration. So a 10 micron from A is not equal to a 10 micron from B. This is very much important to note. We have also measured solid contamination downstream, a nominal filter, downstream absolute filters, and really when we bring that chart with the data together, we see that solid carryover can be significant at many sites, although the filters have been defined as a 5 micron or have been defined as a 10 micron. This only definition or specification of the filter is clearly not enough. You also need to specify performance of your filters, the rating of your filters. It's very much important for a right filter to be installed. A case study for a customer that was having a filter not specified as an absolute filter, so clearly it was a nominal filter, and the filter, the specifications were good but not met. Specification was to have a 5 micron rated filter. Well, the customer had it, but the spec to meet 10 milligram per liter is clearly not the case, because as you can see on the sample on the left side, TSS, total suspended solid, was 93 milligram per liter, and customer was experiencing foaming. He had to reduce capacity down by 15%, and with PAL support we could adapt and retrofit the existing vessel by using some adapters, and very quickly the quality of the amine had improved to values below 5 ppm, and visually you can see a very spectacular switch to a very clear and transparent solution. That has helped the customer to save on capex, no investment required for a new installation, and also he reduced his spend since the filters installed had a higher capacity, so the change out where frequency was reduced. Let's focus now on the other contaminant present is the liquid, mainly free hydrocarbon that appears in the loop because they are not stopped efficiently in the sour gas feed to the absorber. A number of measurements we have done at PAL in several sites found that there are different technologies, conventional cartridges, cyclonic, or separators, and we found liquids downstream of those equipments that was confirmed. And those is justified because the liquid droplets are much smaller, or some technologies can be impacted by variations in flow conditions. By example, especially cyclonic ones, there can be some deviations in turn downs. So definitely a number of those applications do require a high efficient surface treated cartridge coalescer. And also, as highlighted, the liquid carryover is very fine, and this is justified by this study that shows that liquid droplets in a gas stream, especially in high pressure, exist from 3 different root causes. Can be reentrained, can be atomized, or can be condensed. And usually condensation is one of the highly present phenomena in sour gas, and you see it generates very fine liquid droplets, and we measure them, and this is very important to get separated by high efficient separation. Again, a comparative study for liquid removal from gases. We see that not all technologies can handle very fine liquid droplets, and so to avoid carryover. In certain applications, it's fine to remove a bulk of the liquids. There we use some vein pack or cyclonic or demister pad. It helps to reduce the liquids to certain levels. But here, for sour gas amine absorber protection, we definitely need a high efficiency, because the fine droplets that are generating issues of foaming inside the loop needs to be removed very efficiently. To illustrate that, nothing better than a case study for a Middle East gas plant where we did some measurements prior to our intervention, and we find out that the efficiency of existing conventional cartridge coalescer was 44%, maximum it was at 50%, and customer was experiencing continuous anti-foaming and significant liquid carryover. PAL has supported the customer by installing these surface chemically treated retrofit cartridges with very minor adaptation, with some extra bolts and some very minimum adapters, and it helps to improve the removal efficiency of the liquids, as you saw, from 44-50% up to 97% of liquid droplets. This has helped the customer to drop his anti-foam chemical injection by 75%, and the savings of 300,000 were projected per year, which is a 2 months payback here. And we have been also allowed to do that on a second train thanks to the successful experience. Another case study on the liquid side, including that also, is a customer in a gas plant in South America was having issues with foaming frequently in his contactor, amine carryover, despite the customer was having a filter separator on its sour gas and full flow rich side filters. We did some testing, and we highlighted that 1000 ppm of hydrocarbon liquids were carried over to the loop, and these were creating the foaming issues. Then the customer decided to transform and enhance his installation. A new liquid gas coalescer chemically treated was installed on the sour gas. We have retrofitted the existing filters with absolute rated filters on the rich amine and on full flow, and we have installed also a liquid coalescer on the rich amine that helps to remove the hydrocarbon, from which a picture is highlighted here. And you can see here, if we go to the amine loop now, and you can see how the amine is looking like from number 1 and number 2, which we are only removing the solids, but at least the amine is not blackish as earlier. And the outlet of the liquid-liquid coalescer in the rich amine side, number 3, is now very clear and bright. And from that liquid-liquid coalescer, we have the hydrocarbon which we are removing from the top side from the coalescer. In my concluding remarks, I have highlighted here how filtration separation plays a very important role. The role is really key for plant reliability, so you can count and you can be peace of mind about the sustainability of your installation. When defining the performance, you require to be very detailed in order that the technology you plan to install is well defined for your new installations or for enhancement. Another possibility that, by example, PAL offers its customer is the retrofit and the rental filtration services, because they help to quickly implement a cost-effective solutions, and sometimes in waiting of a project for a capital expenditure to be carried out in parallel. So we really partner with our customers to maximize and to really help and support for plant performances. And as I highlighted, we have different channels and routes that can help the customer with rental solutions to have a rapid problem resolution without any capex investment. We have also a retrofit possibility in order to enhance an existing equipment with very minor modifications. When those modifications are difficult to be implemented, then we go for upgrades, where we sometimes require some hot work and some replacement of internals. And a last solution for customers on a more long-term or maybe a new installation is to go through a new equipment that is designed from the beginning of the projects. And this is approach is done on a local capabilities from PAL Corporation with local expertise engineers in your country, speaking your language, and are present not far from you and can visit you very quickly. By this, I thank you very much for your kind attendance. I am happy to receive your questions during the Q&A session later, or later on you can reach out to us. At PAL, we are passionate about solving your toughest challenges. Thank you.
Thank you, Mustafa. Excellent presentation. And we would like to also welcome Onur on stage. Hello, Onur. And we'll now answer your questions. If you haven't answered a question yet, asked a question yet, please type that into the questions tab. So the first question is from Ajaz. 5-micron filters tend to collapse frequently due to clogging of the surface.
Yes, thank you, Marina. This situation can happen on a temporary basis or on a more long-term basis, where an upset is happening on where some operational issues have been met, where a filter which is operating on a normal basis is impacted by some specific contamination at that time. It's good to understand and differentiate that from a normal operating and upset condition. A 5-micron filter will be, of course, more sensitive to contamination because it's a finer rating of filtration. And also, of course, as I explained in the presentation, it depends on how the filter is defined. Is it an absolute or a nominal filter? These are also important that will help troubleshoot the situation. Now, also, when we have such problems, and I understand from the question is more on a surface phenomena, it can happen that liquid hydrocarbon are present in excess, and that can cause a formation of what is called semi-solids, which are solids that are somehow coated by a hydrocarbon, organic matter, and that can be a surface clogging situation. That can be very quickly analyzed by a quick analysis, and we can offer solutions as a rental that can do a service to recover the situation to the initial situation.
Thank you, Mustafa. Question from Dimitrios. Is filtration of the rich amine, as you show, present any health and safety problems?
Yes, indeed. It's a very good question, because nowadays we have also, of course, to work at sites in a very safe environmental policies. Indeed, especially when we have sour systems with H2S presence, it becomes somehow difficult. Although within PAL applications, we have procedures that can mitigate and, of course, reduce the risks and do it in a very safely way. Sometimes this application in the rich amine is very effective, and we try to do to offer solutions that require minimum of the maintenance possible, and then we can work in more safe operations.
Thank you, Mustafa. A question from Armando. Can you please clarify what type of treatments are applied on the surface-treated coalescer in the retrofit study that you have presented?
Yes. Thank you. A very good question. And this is, let's say, PAL as an applied science company. So we do develop our membranes in-house with very own recipes. And we brought this patented technology to our membranes. It is not enough to have a filter membrane operating as a coalescer by means of a special design or by means of a certain setup. Hence, we brought some chemical treatment to our membrane, which we call hydrophobic or hydrophilic membrane chemical treatment to the surface area that helps to change the energy, the surface energy of the membrane, and also to enhance the capacity of capturing the liquid droplets.
Thank you. We have a question in the chat for you as well from Laxma. Filtration 10 micron absolute level means what? Could you please elaborate compared to conventional filter?
Yes, for liquid filters, there are two different, let's say, definitions. A filter rating is defined following PAL by a certain protocol and international recognized testing methods. An absolute filter has this feature, while a nominal filter has an arbitrary definition. Hence, when we speak about a 10 micron absolute filter, means its efficiency is a measurable efficiency, in order we know and we are sure that a certain contamination above a certain size are removed very efficiently and sustainably.
I would like to add here to Mustafa, if you don't mind.
Yeah,
today, filters are mostly regarded as commodity accessories which are used in the process. And once you take a filter in your hand and another one, you harder differentiate. But to the operators in the audience today, you should know that there's a huge material science behind a filter product, and hence, as Mustafa mentioned, it is very important to know how a filter product has been tested, to which method, is it internationally recognized, and therefore the performance is available. Performance results are available. This is very important to qualify a good filter to a non-performing filter.
Thank you for your answers.
Thanks so much.
Next question from Frank. Is rich amine filtration an alternative to gas filtration or vice versa?
Mustafa, okay, maybe he is logged out quickly. Let me take this question. Well, the quick answer is maybe. I know maybe you're not happy with that, but it really depends on the objective. One way to understand is to look at the contamination nature and the type. And if the source of the contamination is known to be coming from the feed gas, definitely having an upgraded filtration system in the feed gas is an ultimate solution. But there's also an impression that better not to touch the rich amine. It's very difficult, but you might be surprised. Filtration solution in the rich amine side is possible and can also potentially solve your problem. So I would say they're not very dependent on each other. It depends on the type and the nature of the contaminants, and both options to be evaluated depending on the thorough analysis in the fluid.
Thank you, Onur. Question from Kek. Does the coalescent filter surface treatment have a lifespan and the recommended replacement interval?
No, it doesn't. The chemical treatment is done during the manufacturing and has a lifespan longer and higher than the normal operating life.
Thank you. And a question from Thomas. How long is the lifetime of the surface treatment of the coalescers? Does it have to be renewed regularly?
Yeah, I understand this is a similar question as the previous one. No, it cannot be renewed, and it is having a longer lifespan than operations.
Thank you. And we'll take one last question from Mihai. Yeah. Sour water tower feed liquid coalescer application in the world. I think that's a question about case studies.
Yes, it's an application for sour water applications, which we know very well. It is in order to prevent any precipitation or deposits in mainly heat elements, like heat exchanger or boilers. And that we are having also applications where the oil removal and solid contamination is removed from the sour water stream. This is something also very standard in our portfolio.
Thank you, Mustafa. Thank you, Onur. And if you have any other questions for you attendees, please address them by presenter so we know who to direct them to. And if you can type your answers in the chat or the questions tab. We would now like to welcome on stage Jacques van Velen, and a brief introduction to follow. And Jacques is the Sales and Marketing Manager for MPR Services, and he will discuss reclaiming amine solvents.
Hello, I am Jacques van Velen from MPR Services. I'm working in the mobile and permanent reclaiming business of gas treating solvents. And that is most of the times amine. The previous speakers in this webinar already explained you what amine systems are and how they are supposed to work. So I will keep that part brief. What I'm going to explain to you is how to make the amine systems work better with less corrosion and less corrosion products. And if you do that, you are reclaiming a lot more than just amine. You reclaim money, you reclaim time, and you reclaim the performance of your plant. Amine systems are closed loops with recirculating liquid in it. Here you see a very simplified amine system. Certainly nowadays amine systems are closed. Hello, I am performance of your plant. Amine systems are closed loops with recirculating liquid in it. Here you see a very simplified amine system. Certainly nowadays amine systems are closed. People do not want to lose valuable amine solvent. That is not considered good housekeeping. It is not good for the environment and not good for the budget. And also, corrosion-wise, it's not a good way of operating. I will tell you later more about this. In the closed loops, gas molecules are picked up at one location and delivered at another location. It looks a bit like another well-known closed loop, your blood recirculation. That is a loop you certainly want to keep closed. In closed loops, contaminants build up. And the better the system is closed, the better contaminants build up. That is the flip side of doing a good job. But you can make or keep a closed loop clean, like your body does, with a kidney, your own reclaimer unit. Which contaminants build up in Amine systems? The typical contaminants are solids, usually corrosion products, hydrocarbons, heat stable salts and degradation products. Paul already told you how important it is to keep the amine clean from solids and hydrocarbons. I am focusing on the heat stable salts and degradation products. The problems related to heat stable salts and degradation products are numerous. These can be corrosion, causing fouling, mechanical failure, and it contributes to foaming. And there can be capacity problems because the amine molecules are tied up with heat stable salts or degradation products. Mass transfer can be obstructed, and there can be viscosity issues and surface tension problems, resulting in foaming and treating problems such as off-spec products. On this picture, you see examples of these problems. You see an example of scaling in a syngas plant on the left top. That is a crystal or crystals formed, contained iron and silicon. Silicon was coming from the anti-foam, which was overdosed. You see some scaling on a regenerated tray. The customer thought they had foaming issues, but it turned out to be scaling. On the right top you see a corrosion of a pump. The customer blamed it on the high biseam levels. In the middle you see some damaged packing material and plug packing material. On the left bottom you see a corrosion of reboiler tubes. You also see the top of a filter vessel with lots of shoe polish and overdosed anti-foam, and filter elements with iron sulfides on it. That customer had a lot of filter changes. I will not make it complicated, but I do want to show you an equation. It is important. It is important to understand why we are reclaiming. Reclaiming means you want something back. Let's use MDEA as an example. It is one of the most popular amine solvers at the moment. And let's use formic acid as an example for the formation of heat stable salts in the MDEA. There are more heat stable salts and amino acids that are strong chelating agents, such as oxalate and acetate, sulfate and bicene and many others. And chlorides, they are a different category. They can harm stainless steel. You see, this is a simple equation. It shows you the two main problems. The amine forms a salt. It is protonated and it is no longer available to pick up gas in the absorber. The stripper cannot revert this reaction. But by reclaiming you can make the amine available again. But equally important, maybe more important I would say, you get rid of the heat stable salts anions, which contribute to corrosion. Let's concentrate on corrosion and on chelation here. The amine system needs to be protected from corrosion. The species which cause the corrosion are the acid gases that the amine system is actually designed for, heat, H2S and CO2. We cannot eliminate them. Therefore, we need to make sure that what protects the amine system from corrosion stays in good shape. That is usually the passivation layer, but can also be a protective layer like cladding, or sometimes the metal itself, like stainless steel. Amine experts already explained that it is important to control the mechanical, physical factors, like pressure changes, flashing, erosion, water hammer. Chemical factors, such as heat stable salts, anions and amino acids, attack and infringe the protection. And the exposed steel will then corrode again by the acid gases. This chelating mechanism is shown on this schematic. Iron from the protective layer, or even transition metals from like chromium and nickel from stainless steel, form a complex with the heat stable salt anions or amino acids. This typically happens in the lower part of the regenerator, in the reboiler also, and in the hot lean amine piping. The complex travels with the amine to the absorber where it gets overwhelmed by H2S and CO2. The iron drops out of the complex as a freshly formed submicronous particle. The free complex former, heat stable salt anion, travels back to the regenerator and does this trick over and over again. As already briefly mentioned, managing your amine quality by losses, unintended, or by bleed and feed, on purpose, is not a way to prevent corrosion. Actually, it happens or is done at a level that is too high and already jeopardizing the mechanical integrity of the amine system and causing daily operational headaches. Coming back to the analogy of blood recirculation, such a strategy of dumping amine would look like the old-fashioned practice of bloodletting, leaching, not a good way of operating. It's much better to reclaim the amine on a regular basis, or even better, continuously, like a kidney. That can be done by techniques like ion exchange, electrodialysis, or vacuum distillation. In amine solution, MPR Services uses a special ion exchange process, since it can clean to very low levels of heat stable salts and amino acids. Reclaiming is normally done online on a slipstream, while the amine system is operating. A German refinery contacted us. They had corrosion and plugging issues. The technology group of the oil company had done amine analysis and reported colloidal iron sulfides, high iron solubility, high levels of bicene and heat stable salts, and because of that the pH was low. The chromium level was high, and not surprisingly there was a lot of suspended solids. The amine color was green. The complete reclaiming job took less than a week, and as you can see in the table, the heat stable salts and amino acids were greatly reduced to below most of the common guidelines in the industry. For example, 1000 ppm for formate. The color became rather white, and already on the job the suspended solids level was much lower. The iron solubility was reduced from an extremely high level of 722 ppm to below 20 ppm. A syngas plant had plans to increase the production. The amine system, however, was the limiting factor. Despite the fact that they replaced a lot of amine every 2 weeks, they constantly had a level of heat stable salts of over 10% as amine. That limited the capacity of the amine and the activator. The iron hexacyanate levels were over 1000 ppm. With the frequent amine dumpings, they were also throwing away the amine systems itself in a soluble form. Instead of a complete revamp, it was decided to install a permanent reclaimer. The permanent unit brought down the heat stable salts, as you can see in the graph. It reduced the levels of formamet and gave back the amine and activator that was earlier tied up. The iron and the iron cyanide levels went down to less than 10 ppm. But most important was that syngas capacity could be increased. Any questions?
Thank you, Jacques. Excellent presentation, and we'll see what questions we have for you. Our first question is from Josefa. How many units of pH increase can we see after removing about 0.5 WT% of HSS?
Yeah, I'm sorry, I cannot answer that like that, because the heat stable salts do contribute to lowering the pH, but there is also acid gas in the amine. So when you have not removed your H2S or CO2 well enough, that will also have a big impact on the pH, of course. But generally spoken, for example, if you have a well regenerated MDEA, you would like the pH to be around 10.5. And if you see it lower, like lower than 10, for example, then it could be an indication that there is something wrong with your heat stable salts. But you need to do proper analysis of the amine solvent to really say if the heat stable salts is causing this and if it is a problem.
Thank you, Jacques. Next question from Dalibor. What does it mean, remove H2S enough?
Yeah, I'm just wondering what this relates to. Of course, the amine system is meant to remove H2S from the sour gases. So if it doesn't remove it enough, then your gas will be off spec. So your amine system needs to do a good job of removing H2S.
Next question from Amela. What is the maximum limit for H2S?
H2S in the amine or in the gas. You could say the maximum limit for the H2S depends on what you're going to, in the gas, depends on what you're going to use the gas for, of course. If you're going to liquefy it, you have to remove it almost completely. And it also depends on the environmental specifications that you have, if it needs to be 30 ppm or much lower. In the amine itself, the H2S depends on what kind of amine you're using, what you can have there. So what your normal lean loading would be. Lean loadings in primary amines are higher than it is in tertiary amines, for example. So there's no general answer for that.
Like they usually aren't. Thank you. Next question from Arash. What do you suggest to be done with concentrated amine effluent from amine vacuum distillation reclaiming process?
Yeah, once you have done the vacuum distillation process and it is concentrated effluent, you have to get rid of it, of course. And that also depends on where you are and where you're located and what you can do with it. Some people can burn it. Some people can dribble it into a treatment system. But it can be difficult, of course. So that is one of the difficult things with vacuum distillation. Typically, it is not a lot of effluent that you have from vacuum distillation, but it is hard to handle. Ion exchange has a lot more effluent, but it is easy to handle. You can typically send it to the wastewater system. And the EDU technology is somewhere in between those two.
Thank you. Great answer. Next question from Omar. Can HSS formation be prevented by controlling reboiler temperature for generic MDEA without additive?
Yeah, that is a good one. Lower temperatures can mean that you have less heat stable salts build up, but it depends where your heat stable salts buildup comes from. So if you're operating a cat cracker or a delayed coker unit and you have cyanides in your gas, then those will get into your amine and become thiocyanate and formate. From that mechanism, it will not, lowering your reboiler temperature is not going to protect you from that kind of mechanism, for example. But if, like Philip said earlier, if it is because of oxygen getting into your amine, then it could help if the reboiler temperature would be lower, because the mechanism is that the amine molecule breaks and the alcohol group breaks off, and therefore if you can prevent that by lowering the temperature a little bit, that would help. But Philip also said it already happens at 60+ degrees C, so the influence is limited. But certainly do not run too high reboiler temperatures, because that can cause a lot of degradation products.
Thank you, Jacques. We'll take one more question before moving on to the next presentation. And if you have more questions for Jacques, please type them in and he will answer them in the questions tab. Question from Antal. The rich amine chloride content is a problem during purification. Is it a problem?
The rich amine chloride?
Chloride content is a problem during purification.
No, a chloride in amine is a problem, of course. If I don't know, it's rich here, but probably it's rich. If it is in the rich, it will also be in the lean. It's an heat-stable salt. It will be recirculating in the amine. So it is problematic. The metallurgists are not all on having the same standards. Some say 100 ppm is the guideline. Others say 200 or 300 ppm, but it's always on the lower end that you want your chlorides to be controlled, because it can cause cracking type of corrosion in stainless steel. You don't want that to happen. So yes, I would say it is a problem, chlorides.
Mm-hmm. Thank you, Jacques. And our last speaker of today is Mike Shailen. And he's the principal engineer at Amine Experts, and he will talk to us about the effects of hydraulic flow on amine plant corrosion.
Hello, everyone. My name is Mike Sheelan, and I'm a senior principal engineer with a company called Amine Experts. And the topic of my presentation today is the effect of hydraulic flow on amine plant corrosion. As we've seen from the other presentations, corrosion in amine systems is a common problem. Most of us are well aware of the importance of system and solution management on reducing the corrosivity of the circulating solutions. We've already discussed the importance of heat-stable salt management, filtration, good inlet separation, but we also have to control acid-gas loadings, temperature, and flow velocity, all while considering the proper metallurgy. Experience indicates that rather than being a problem throughout the entire system, corrosion in amine systems tends to be highly localized. And one of the reasons for localized corrosion effect is the release of acid gases from that circulating amine solution. Both a temperature increase and a pressure reduction can shift the equilibrium sufficiently to allow acid gases to escape from the solution, and this escaped acid gas has the potential to attack the steel, depending on the temperature and the location that this acid gas breakout occurs. One pressure change that occurs but is often overlooked is caused by hydraulic flow effects within the amine unit. Hydraulic flow effects can lead to liberation of acid gases, and depending on the location of the liberation can lead to aggressive corrosion within the system. Let's delve deeper into the problem. Whenever we talk about hydraulics in a system, Bernoulli's published work from 1738 must be considered. According to Bernoulli's equation, the sum of the static pressure component plus the dynamic or velocity pressure component plus the hydrostatic pressure component are a constant along a streamline. So the pressure is a constant at point 1 and at point 2 in this diagram. Because the velocity effect is squared, it becomes a very important component of any discussions around changes in dynamic pressure within a system. According to the equation, the pressure sum at point 1 is the same as at point 2 along the streamline. Now, since the diameter of the piping at point 2 is less than at point 1, the velocity of the fluid must increase from point 1 to point 2, resulting in a dramatic increase in the dynamic pressure component of the equation. Now, in order to satisfy that equation and keep it a constant, therefore, the static pressure component must drop precipitously as well to keep that sum a constant. Thus, Bernoulli's principle that states for a horizontal flow, an increase in velocity must always be accompanied by a decrease in pressure in order to satisfy conservation of energy. In much simpler terms, the total system pressure at any point within the amine system is the sum of a static pressure component and a velocity pressure component. Anywhere in the system where the amine is subjected to a change in velocity can contribute to the potential for acid gas to break out of solution if the drop in static pressure is enough to upset the system equilibrium. Now, this effect will be worse in locations with higher loading, higher temperature, or higher turbulence. The first example is the case of contraction at a tube sheet entrance. The bottom figure shows the effect of entrance conditions of amine in a tube with a location of severe necking of the fluid known as the vena contracta near the entrance. At this location, the velocity of the fluid is increased, resulting in an increase in velocity pressure. The upper part of the figure includes the energy line, or EL, as well as the hydraulic gradient line, or HGL, relative to that entrance condition. The energy line corresponds to the total pressure in the system at any point along the flow, while the hydraulic gradient line corresponds to the static pressure at any point along that flow. The greater the distance between the energy line and the hydraulic gradient line, the greater the velocity pressure, and subsequently, the lesser the static pressure. Now note that there is a small permanent head loss, but also a rather large temporary static pressure loss caused by that vena contracta. At the vena contracta, which is the necking down of the fluid stream at the entrance, the static pressure can drop so low as to reach a point where the pressure is below the equilibrium pressure of the acid gas in solution, resulting in breakout of acid gas in the dead zone around that vena contracta. This acid gas then migrates along the tube wall until it reaches a transition zone where conditions are conducive to corrosive activity. Generally, our goal is to maintain tube velocities in the range of 1 to 1.5 meters per second, but at the vena contracta, it's not unusual to have velocities in excess of 2 and even close to 3 meters per second, which can make for accelerated velocities within the tube that are in excess of our general guidelines. Now note that head loss is a function of velocity, the gravitational constant, and a factor K. Now the intent of a hydraulic engineer is to design a system in which the K value is as low as possible to minimize the effects of entrance conditions on static pressure changes and release of acid gas at this location of the tubes. Entrance designs can not only reduce the head loss via reduction in the KL value, but they can also reduce the difference in cross-sectional area between the entrance and the vena contracta. If we look at the bottom right picture, which is called a re-entrant condition, which is consistent with a tube sheet that has protruding tubes coming out of the tube sheet, you can see that it has the smallest area factor, which means the velocity of flow will be the highest, and it also has the highest KL compared to the other flow conditions, specifically looking at the bottom left, which is a sharp-edged or flush mount tube inside a tube sheet. Now the combination of the higher reduced area and the higher K value can cause excessive velocities, which means a high velocity pressure, which also means a low static pressure. And this static pressure drop can be severe enough that we can flash acid gas out of the solution as it enters the tubes. And we tend to see the corrosion manifesting itself around 18 to 20 pipe diameters from the entrance of the tube. So that means we want to have the tube sheet that looks like the picture on the left, with slightly rounded entrance conditions as opposed to the protruding tubes in the tube sheet to the right if we want to reduce corrosion within the system. Acid gas breakout effects are not as severe in sudden expansions, as you can see from the drawing below, where we go from a smaller diameter pipe to a larger diameter pipe. Inside the larger diameter pipe, the flow velocity will naturally slow down, which means that the difference between the hydraulic gradient line and the energy line reduces, and mostly we'll get potential acid gas breakout from that head loss at the entrance. And if there is acid gas breakout, that acid gas tends to find the dead zone, which is the location immediately downstream of the expansion, and there's a potential for corrosion at that location. This particular example showed the corrosion that occurred at the exit of a thermosiphon reboiler. The tube and the tube sheet showed quite severe corrosion pattern because of the high exit velocity achieved inside a thermosiphon reboiler. The only way that we could correct the problem was to grind the tubes so that they were flush to the tube sheet exit, and that definitely improved and reduced the corrosion potential inside this system. Threaded connections are generally not seen in amine service, but in some older facilities that we visited, they are still present. The area of low pressure caused by the non-streamlined flow over a threaded joint causes acid gas escape with migration of the acid gas along the threaded connections and subsequent corrosion of the threads. Threaded connections are more prone to eventual failure because the walls are thinner than the pipe. And the cure then is obviously don't use threaded connections in amine service. This is another example of non-streamlined flow caused by an obstruction in a horizontal pipe. The obstruction causes a reduction in flow area, which means that you generate a vena contracta, and at this location you can break out acid gas. The acid gas tends to migrate just past the obstruction, and in this case it's the downstream side of a valve body, and in many cases we get very severe corrosion of the valve body downstream of that obstruction. And this is especially severe in cases where we have high CO2, high temperature, or high velocity. These pictures all show corrosion damage on valve bodies downstream of an obstruction or on the downstream side of a level control valve. The upper right picture shows an absorber level control valve with some corrosive attack. All the other ones show quite major attack on the downstream part of the valve body. And the reason why the flash drum level control valves are much more severe as far as the corrosion rate goes is because that level control valve is downstream of the lean-rich exchanger, and the temperature is much hotter at this location, so any corrosive attack will be accelerated. All valves do work best when installed in a non-turbulent flow condition, so that means a minimum of 5 nominal pipe diameters both upstream and downstream of the valve to reduce the chances of turbulent flow through that particular valve. This is a very interesting example. It was corrosion of tubes in a lean-rich exchanger, and the tubes are corroded right below the entrance point of the hot lean amine into the shell and tube exchanger. The previous tube bundle had lasted 13 years, and they replaced the new bundle. They ascribed the corrosion to erosion corrosion, and therefore decided to weld a plate at the entrance to protect the tubes below that plate from erosive attack of hot lean amine entering the shell side of that exchanger. Unfortunately, after they installed the plate, the plant had a tube failure within 6 months of startup, and they called us in to ask if we could figure out what caused the corrosion. Now, when we looked at the original tube bundle, the corrosion damage on the tubes was the underside of the tubes, not the top part of the tubes. So since it was on the underside of the tubes, we really wouldn't expect erosion. And what we determined was that the pitting on the bottom part of the tubes was caused by the flow effect around the tubes of that hot lean amine. There is an entrance condition, we break out acid gas, and the acid gas finds a dead zone, which happens to be the underside of the tubes. By welding that splash plate, they created a massive dead zone underneath the entrance. So rather than just destroying the underside of the tubes, they had severe damage over the almost the entire tube sheet below the entrance. So they didn't believe our explanation and decided that they were going to reinstall the splash plate. And we asked for a compromise, and we said, if you're going to keep the splash plate in, please drill some holes in it to dissipate some energy, but still keep some fluid going through that plate so we don't create the big dead zone. And that seemed to correct the problem, as that next bundle lasted well over 10 years. 20 years later, we came across exactly the same problem. Tube failure that was diagnosed as erosion corrosion. In the upper pictures, we can see a welded plate that was installed to protect the tubes. And within 6 months of starting up the plant again, you can see the severe corrosion that occurred below that welded plate. The bottom two pictures show another facility that also had corrosion and decided to install a plate, but did follow through with the guidelines to drill holes in the plate to dissipate the energy, but also keep those tubes properly wetted. And that was successful in achieving a long life. And the center picture shows us another welded plate that not only have the tubes been corroded, but also the plate itself has been severely damaged. So welding a plate in a lean-rich exchanger really needs to be discussed before deciding to install one. Two means of reducing the potential for pump impeller and pump suction corrosion is to try to mitigate acid gas breakout before the pump, and that's by using either a long radius elbow or trying to have 7 to 9 pipe diameters of a straight run of pipe upstream of that pump. From the upper picture, we can see that at an elbow, the area of highest flow, and thus the area of highest pressure, is the outer diameter of the elbow, and this is the location where we might see erosion corrosion. If you see corrosion on the inner diameter of the elbow, it's generally related to acid gas breakout because of the lower pressure drop conditions at that location in the pipe. So if you have corrosion on the outer elbow, it means you've got erosion corrosion, and if the inner part of the elbow is damaged, it's generally related to acid gas breakout from hydraulic flow effects. This picture from a large gas plant shows the very poor hydraulic design of the piping upstream of the solution charge pumps. It's quite clear that there are far too many bends in the piping, and they were a major contributor to hydraulic flow changes and acid gas breakout that caused severe corrosion at this location in the plant. In conclusion, we'd like to say that all plant and equipment design should be reviewed by a competent hydraulic engineer prior to manufacture of the facility. They can check the design to make sure that there's no locations where we have severe hydraulic flow effects, and if we can eliminate those points, we can reduce the overall corrosion potential in our system. Every one of these examples was experienced in actual plants, and we did use the corrective measures that were mentioned to overcome the corrosion problems that were encountered. Thank you very much for your attention to this paper, and we look forward to any discussion and any questions you might have on the topic. Thank you.
Thank you very much to Mike Sheelan, and we would like to welcome a representative for Amine Experts to answer any questions for Mike. And if you do have some questions for Mike, please type them in to the questions tab or the chat if that's preferable. Welcome back, Philip.
Thank you. I'll do my best to answer any questions from Mike. He will also be online later at the second seminar.
And the second seminar will be starting in just under 5 hours. And it will be live, similar to this one. So you're welcome to share the registration page with your colleagues. I already posted it in the chat, but I'll post a link to it again now. And everybody who has registered for the first session but hasn't attended it will be registered for the second session. So just keep an eye on your emails for your access link. And we have a question for you, Philip, from Sukant. For a straight length of piping, corrosion most prevalent at well joint and heat affected zone. Lean amine with 6,000 to 8,000 ppm. Does this also occur due to flow turbulence at a well joint?
So I probably need a little bit more detail, but the you can, if you have attack on a weld, it can be because of the mechanism, the hydraulic mechanisms Mike has been describing now. It could also be due to something in the weld. So if the weld is not constructed in a good manner, or you know, if it's not post-weld heat treated, you could get hydrogen-induced cracking. So there's a couple of different things that could be causing a failure in the weld. But yeah, normally if you have a straight length of pipe and the only thing in it is the weld, that's the area where you will have the pressure drop and are most likely to have a corrosion occurring as a result.
Thank you, Philip. And I guess for a deeper discussion, Sukant can contact you directly. And our next question is from Catalin. Plate heat exchanger used as real boiler, is that a good option?
Well, we don't see that a whole lot. I would be disinclined to do that because you're quite a significant pressure drop in a plate and frame exchanger, and you're also dealing with, you know, a service that's traditionally quite fouling. Normally we see plate and frame exchangers in the lean-rich exchanger for non-fouling service, so not refineries, not steel mills. And if you do have plate and frame exchangers, they're normally spared just because of the likelihood of it getting fouled up and needing maintenance is fairly high. But a couple of plants will just put a single plate and frame exchanger in and have really quite some problems as a result. So yeah, no, we haven't seen it. Off the top of my head, I don't think it's a good idea, but we probably need to think about it a bit more.
Thank you, Philip. I think that was our final question for Mike's presentation. We would like to welcome the rest of our speakers on stage now for a quick summary of the event, and we'll have a brief roundtable discussion. Thank you, and would like to thank all of our speakers for amazing presentations and answering all of our attendees' questions. If you would like any more information, you can see the email addresses and the phone numbers of our speakers, so you can follow up with them direct. And we'll just do a quick run through the polls and see what the answers to those are. And we'll do them in order. So to the question, where have you experienced corrosion on an amine plant? The most popular answer was reboiler and associated piping. Does that surprise you, Philip, or is that what you would expect?
Yeah, that's what we'd expect. Also, sort of from what we found in the database, like most of the instances of corrosion were in the reboiler and in the reboiler drain line. So that was really kind of in line with our experience.
And the next poll answer was, what does the corrosion in your amine system look like? And the most popular answer is pits, so pitting corrosion.
Yeah, also not a surprise. I'm not very surprised today. I mean, it's yeah, the CO2 attack on the metallurgy inside amine systems and that sort of pitting type corrosion is really probably about half of what we see when we are troubleshooting on corrosion problems. So
And
it's really a problem.
thank you. And 2% actually answered that their corrosion looks like something else. What else could it look like?
There's a large number of possibilities, really. It's so there are many things, strange things that can go wrong. It's yeah.
It's very interesting. Colin, you had something to add there?
I was going to say that's quite a subjective question. It could look like whatever you think it looks like. Yeah. Corrosion comes in many forms, like Philip said.
It does indeed. And the next poll answer was during Tim Miller's presentation. And majority of people have actually not experienced an extended outage or turnaround due to unplanned maintenance. However, 35% of them have. Colin, can you comment on that?
Yeah, I mean, we have some experience of applications where we're addressing discovery scope. So one example was an Amine reboiler upstream, obviously of the inlet into the column, where they had leakage that they weren't aware of. So when they then opened the column subsequently in the outage, they found some very aggressive carbonic acid corrosion that had taken place at the entry point from the reboiler into the column, where you're getting breakout. So for them, that was a totally unexpected discovery during the outage that they then had to address, because it caused significant metal wastage, and they had to ensure that the column was still fit for purpose to operate through to the next turnaround. So often it's it's not due to the fact that you're not monitoring the vessel, or you're not carrying out the correct type of RBI. Sometimes the situation can just be unexpected.
Thank you, Colin. And when we asked the question about people's current metal wastage mitigation strategy, the majority of them answered that it was welding repairs and replacement. Mm-hmm. Do you think replacement refers to replacing entire vessels in this case?
It can be. I mean, we've seen situations where vessels have been replaced, sometimes not just because of the fact that they've discovered challenges with corrosion. Sometimes it's been to increase the capacity, to remove a bottleneck in the process, to provide a bypass if there is, for example, a failure in one of the units. Section replacement is pretty common as well, and I think if planned correctly and everything else, then that can be built into your turnaround and outage. I mean, what we are trying to achieve with the corrosion barriers we install is obviously the avoidance of having to go to either of those major mechanical or replacement strategies or activities. And often, where the column is situated, the plant around it, the difficulty of extraction and installation, the extra piping you have to do, the tie-ins and everything else, can mean that the time required to do that type of work, and obviously the craneage, to bring the stuff in is extensive. So being able to avoid that can be of great value, particularly if you have high opportunity costs from the plant.
Thank you, Colin. Our next poll question was about the filtration system. So is your actual filtration system delivering on its expectations? And the majority answered that it works fine and contributes well to the operation. But the next most popular answer was, we have filters, but still foaming is recurrent. Would you like to comment on that, Mustafa?
Yeah, definitely. Well, that's a great news that a lot have selected number one, meaning that filtration, people are aware that filtration is an important role inside the loop and help to prevent big issues and keep the contamination controlled. Fact that people with filters but still experiencing foaming is an alarm that the filter needs to be looked at in more details, focused, in order to do some analysis and some troubleshooting on the filtration system.
Thank you for that. And the second question was, what protection for liquids carryover do you have in place on sour gas feed? And the majority answered that they use a conventional separator, such as a knockout drum, mesh, or vane pads. Is that what you would expect?
Yes, indeed, because we see that also in the field, there is somehow a transitional situation happening with the upgrade of this kind of separation technologies. Usually customers neglect a little bit the sour gas coming contamination that is carried over inside the loops, and with our field exposure to the customer, we see that there is more and more importance accorded to that stream which is carrying over the contamination.
Thank you, Mustafa. Our next poll question was, what do you consider the most common problem in Amine systems? And the most common problem in Amine systems was found to be foaming, and then corrosion being the second most common. Could you please comment on that, Jacques?
Yeah, well, it's not surprising me. They are related, though, as many of these contaminants are related to each other. Foaming is typically introduced because of surfactants, the contaminants in the amine, but it is aggravated and stabilized by particles, typically small particles, and those are again the corrosion products. So corrosion and foaming, good filtration, and preventing corrosion are things that that are really related and should be addressed together. So taking out the species that cause the corrosion, preventing the system from having corrosion, and preventing the system from having species in it that cause the foaming are all important. That's why we do this holistic approach, I think.
It's very true. And the next question was, what do you think should be the key driver for keeping the amine clean? And the two most popular answers here was to assure the on-spec gas production of the plant and to prevent mechanical failure by corrosion. Would you agree with that?
Yeah, and I'm glad that that the people are saying that, because very often still people are looking at just the cost of running the amine system alone, like the steam or the filter consumption and anti-foam additions, for example. But well, most important is of course making sure that you can produce the gas and the mechanical integrity of your system in the long term, not the day-to-day operational issues. They are important, but the long term and the production should be the key drivers.
Thank you, Jacques. And our final poll question was during Mike Sheelan's presentation. So if Philip can comment on that and also summarize the event. So overwhelming majority of people have seen corrosion in welds and pipe elbows. And I think we've just lost Philip again. It's all right, internet connection, it happens. We can comment on that poll personally by email if you would like more information. And I'll just bring up again the contact details of our speakers. If you have any additional questions, you are welcome to contact them directly. And if you or your colleagues would like to attend the next session, which will take place in 4.5 hours, we'll just post the registration page one more time. So having said that, again, thank you to our speakers.
Pleasure.
Our pleasure. Thank you.
Yeah, you're very welcome. Thank you for your time and attention.
Thank you. And we'll see our speakers again in a few hours, and we may see some of you again later today. Just to remind you, the recording of this session will be available on this exact same link. It will just take maybe up to an hour for it to become available. So once we end the event, it will say the event is ended. But if you refresh in about an hour later, you will see the recording. You will also receive the link to recording by email. It may go to your junk or spam folder, so let us know if you haven't received it. So have a great day, everybody, and goodbye.